Okay, so homework number 3 having to do with reactors is due before class on Wednesday. You submitted homework 2 before 11:59 p.m. on Friday, right? So I think that the grader will probably get that finalized within the next couple of days. And the other announcement is that the class on Friday is going to be an online video. And then if you're able to join the presentation today at 2 o'clock next door, right after this class, is another faculty candidate who's going to be speaking about coagulation flocculation and then an overview of her research interests and past experience. So you're welcome to attend that if you're interested and available. If you do the assignment that's on Blackboard associated with that, it's optional, but it's worth 10 homework points. Bonus. Okay, so today we're going to continue talking about reactors, and specifically we're going to talk about ways to characterize whether they're ideal or how far away from ideal they are. So C curves and F curves exist as tools for us to investigate how reactors in the real world are behaving. So any questions related to the announcements before we start talking about reactors? Okay, so we want to know how good is a reactor. You know, completely mixed flow reactor assumes that as soon as the water comes in, it's instantly dispersed everywhere. And not any reactor in the world is going to be perfect like that assumption. So we can do tests to evaluate, for example, how quickly the water is dispersed when it comes into a completely mixed flow reactor. And one of the tools we use to test that is by putting in some sort of a signal, like a tracer. So we could, for example, by putting a drop of dye into a liquid, we could see how quickly will it disperse. So you can see that right now, this tracer is not completely dispersed into the water that it's been dropped. So what if we put a mixer down in there? Like if we put a spinning impeller, and then we put the dropper of dye in, it would probably not look like this for very long. Like we'd have to use a high-speed camera potentially to get a picture of, you know, some of the dye is isolated, certain zones don't have any dye. So just the first thing I want to introduce is the idea that a conservative tracer is one that isn't reacting. So we wouldn't use, if we just want to like characterize the mixing behavior of the reactor, we wouldn't use something that's going to be decaying, because then we wouldn't be able to know if we don't see the reactor at a certain place, is it because it's decayed or is it because it hasn't mixed correctly yet? So to avoid that ambiguity, we instead use conservative tracers, which are inert and aren't going to react. And an instantaneous signal is one that we can deliver all at once. So when you put a drop of dye into this glass, you're effectively delivering all of the dye instantaneously. But what if you were trying to use like a really thick liquid, like very viscous, and it's dyed black, but you're trying to pour it, and it's pouring slowly, and it's not getting in there all at once. It's just kind of like gradually getting in there. Well, then that would also confuse our effort to characterize the reaction, or the reactor, because we wouldn't know if we don't see it because the reactor isn't mixing well, or if it's because we didn't get the signal in instantaneously. So for us to really do a good job to just focus in on just the mixing behavior of the reactor, we want our signal to be both conservative. It's not talking about politics there. It's just talking about it doesn't have a reaction. And instantaneous, meaning we can deliver it to the reactor instantly. The reactor may not mix it instantly, but we are delivering it to the reactor instantly. So any questions so far about conservative and instantaneous? Okay, so the simplest type of reactor, remember, is a mixed batch reactor. A mixed batch reactor doesn't have any flow going in, it doesn't have any flow going out. It's just we put the stuff into the reactor, start stirring it, and then the reaction begins. And so if we have this instantaneous signal that we put into a mixed batch reactor, we put it in instantly. If you wanted to graph what would be the concentration over time versus the initial concentration, so it would be 0 at first, like there's no concentration, until all of the sudden, instantaneously, it's going to go up to 1, meaning that the concentration at a given time is equal to the initial concentration. So this vertical line would imply that it's perfectly mixed. So this is what you'd see for a mixed batch reactor that is perfectly mixing. So to do that, this impeller would need to be spinning pretty quickly relative to the volume. Like if it's just kind of dawdling and spinning slowly, then it wouldn't have this vertical line. So anybody here been to Lake William before at Barbersville Park? They've got like some aerators in Lake William. I was there yesterday. I noticed that near the aerators the lake's not frozen. But like if I poured in a bunch of food coloring into Lake William, it's not instantly going to change the color of the whole lake everywhere because it's not mixing enough to do that instantly. This curve, a C curve as this is called, concentration versus the initial concentration, will help you to understand the mixing behavior. So we call this a C distribution or a C curve, and it's just a way of characterizing how the concentration changes after you inject the sample. So you'd put it in at time 0, and then you'd start taking the sample out starting at time 0 and then thereafter to see how the concentration is changing over time. So that's a mixed batch reactor. This is an ideal C curve showing perfect mixing. A plug flow reactor, I think you maybe remember that what we assume for a plug flow reactor ideally is that it has no longitudinal mixing, meaning longitudinal is in the direction of flow. So as the water is going horizontally through this pipe reactor, it's not mixing side to side. All of the flow is staying together until it exits. So the amount of time that any particle spends in a plug flow reactor is equal to the hydraulic residence time. So all of the elements coming in and going out spend the same amount of time in there. Now, by the way, different books and different equation sheets have different symbols that they use for hydraulic detention time. Sometimes you'll see theta for hydraulic detention time, T sub theta, or T with a bar over it. It basically means how long the liquid spends on average inside of the reactor. And you can calculate that by the volume divided by the flow rate. So if volume is cubic meters, for example, and flow rate's cubic meters per second, then your residence time would be in seconds. So just another way to think of the residence time is if it was empty, how long it would take to fill up the reactor at a certain flow rate. So whether it's a plug flow reactor, completely mixed flow, residence time has the same definition, hydraulic residence time. The residence time of the liquid that's going into the reactor. This is what a C curve would look like in a plug flow reactor. And this is different. This isn't the same C curve I showed you before. Before it went up to 1 and then stayed at 1. Here, it starts at 0 and then it goes to basically undefined or infinity, meaning that all of the concentration is coming out all at once. So it's not dispersed at all. So think about if you put some food coloring in here at the inlet, all of the food coloring, like if it was from a dropper, it would come out in the same drop if there was no mixing inside of the reactor. It would just come out all at once. And so you wouldn't be able to necessarily define the concentration of the dye because it wouldn't have mixed in the surrounding fluid. So that's why it's just a vertical line at the hydraulic residence time, assuming that there's no mixing. So let me give you today's in-class exercise, and what we're going to do is I I'm going to ask you to speculate here. Now, it's something that you haven't necessarily ever heard before, C curves, and so you can be forgiven if you get it wrong. It's very low stakes, but I do want you to just think about, for these reactors, what would the C curve look like if there has been some mixing and dispersion? So in other words, if it's not a perfect reactor, what would the shape of the C curve look like? Blood flow reactor with some mixing and dispersion. Where ideally it would look like this, where it all comes out at once. But instead of coming out all at once, it mixed a little bit. So what would the C curve look like? Did everybody get a copy? You need one? Okay, so this is what the C curve would look like if it had been spreading out a little bit. It would look like, what's that called? A bell curve or a normal distribution. And the reason for that, I've just drawn a little illustration on the whiteboard showing, here's our slug of tracer. And if we acknowledge the fact that dispersion is a real thing and it's having an effect, then even without mixing, like without bulk mixing, which is called advection, the dye is just going to naturally spread out because of dispersion. Like this room that we're in right now, if I cut off the fan and there was no airflow in or out and we held very, very still, if none of us moved and it was just kind of like dead air, I could open up a canister of tear gas in the corner of the room and eventually it would get all of us. It's not going to just stay in the corner of the room. It's going to spread out. That's dispersion. So here, it's just like the molecular movement is going to cause it to disperse through the fluid. So that's one of the things that we're assuming happens in the real world, is that the conservative tracer disperses in the fluid. But then on top of that, there's advection. So if I opened up the tear gas canister in the corner, the fact that the fan, the ventilation is running and I'm moving around, that's causing like a little bit of swirling and mixing of the air. So that bulk mixing of the air, which is advection, would also help to speed up the dispersion of the tear gas. So the same thing is true here. So far, the sketch that I've shown is only showing dispersion. But now also think about like water going through this pipe, depending on its velocity, it may have like some turbulence. Like water doesn't go the same speed everywhere in the reactor. Even if it's going in laminar conditions, it still has a velocity profile that's faster in the center of the pipe compared to the edge of the pipe. So that is going to cause the tracer to get deformed, even if it's laminar conditions. If it's turbulent, it's going to be even more mixing. So the real world is going to cause the fact that these ones that are ahead of the average, they somehow got ahead of most of the other particles. There will be some molecules of the dye that exit the reactor before the hydraulic detention time. they spend less time in the reactor than the average particle does. And so most of the dye here is spread out over the average. And then you can get a sense that probably these lagging tracer particles are the ones that, maybe they were near the edge where the velocity was less. And that's why they spent more time in the reactor and they go out towards the last. So yeah, that is the C curve. And they help us to know whether a reactor is mixing a lot or a little. So think about the shape of this distribution. The faster you go, the more mixing there will be, and this bell curve is going to be more wide if there's more mixing. So the closer it is to ideal, it's going to be steep and narrow. If it's actually behaving as a real plug flow reactor, it would be more peaked, and if it has a lot of mixing and short circuiting, then it would be more of a broad bell curve. Okay, so we talked about C curves. Now here's an F curve. In a plug flow reactor, an F curve is going to show like this. So an F is the fraction of the tracer that has exited the reactor at any given time. So if it's an ideal plug flow reactor, it would be that none of it has exited, and then all of a sudden 100% of it has exited. So that's ideal behavior in a plug flow reactor. And the way that we calculate, if numerically we're going to do a graph of F, is it's the initial amount minus the amount that's remaining in the reactor divided by the initial amount. And so in the plug flow reactor, it's just all at once. We did an experiment like this when I was in graduate school at Purdue. We went to a wastewater treatment plant. We poured in a tracer into the wastewater treatment plant that was fluorescent under ultraviolet light. And our professor had an instrument where we could take measurements, and so we stood out at this wastewater treatment plant taking samples, I think maybe every 10 minutes, and trying to estimate the fraction that had exited the reactor at any time. I should look and see if I still have that data. It would make for a good homework assignment, I think. But I think you get from a sense here that if it wasn't ideal, it wouldn't be vertical, it would be maybe S-curved, as they say. We can also do C curves and F curves on completely mixed flow reactors. So a completely mixed flow reactor does, unlike a batch, have flow in and flow out over time. So what happens when you add a conservative tracer instantly to a completely mixed flow reactor? What is the in-class exercise is asking you here on question 2. What do you think the C curve is going to look like for a completely mixed flow reactor? Now, remember, the axis is time on the horizontal axis and C versus C naught on the vertical axis. So what is the shape of that going to look like for a completely mixed flow reactor? Just speculate. This is what it'll look like. It starts at 1, and it's going to be gradually going down as you're flushing it out of the reactor. So it'll have this characteristic shape. So a completely mixed flow reactor, remember that concentration is the amount divided by some volume of a reactor. And the tracer goes in instantaneously, but then we're not putting more and more of the tracer in. We just put it in as a pulse at time 0, and then it's only being flushed out after that. So we have no in, and we have the rate that the signal is going out, if we're thinking about this in terms of mass balance. So we could say that the change in amount over time is the amount divided by the volume times the flow rate. with a decrease there, so negative sign. So the C curve in a completely mixed flow reactor, if we integrate that, what we end up with is this equation that we've seen before, where the concentration is related to the initial concentration, and then E to the minus T divided by the hydraulic detention time. So T bar, remember, is the time that the average fluid particle is going to spend inside of the reactor. So the C curve in a completely mixed flow reactor, when you get to the average hydraulic detention time, is 0.368. So what that means is that you can't flush it out completely. If you put that tracer in, so if I inject dye into the completely mixed flow reactor, and maybe it has a volume of 1 cubic meter, and I've completely flushed it out, so I've put in a new cubic meter, it's still going to have 36.8% of the dye still in there, because some of it is mixed. So you put in a little bit, you have a little bit going out, you have a little more going in, have a little bit more going out, but by just flushing it for the hydraulic detention time, you're not completely removing all of the tracer. There's still going to be 36.8%, assuming complete mixing and perfect behavior inside of this completely mixed flow reactor. I recently changed my transmission fluid on my car. I have an automatic transmission. My car is at about 100,000 miles, and if you drain the transmission, you can only take out about 5 quarts of transmission fluid, but the capacity of the transmission is about 12 quarts of transmission fluid. So like 7 of them stay in the transmission. So my strategy is I drain it, put in, replace the new 5 quarts of transmission fluid, run it for like an oil change duration, 7,500 miles. Then next time I change the oil, also change the transmission fluid. So I'm gradually flushing out the transmission, and it's going to, even though I've taken some out and replaced it with the fresh stuff, it's going to take more than several changes to get it back to being like completely fresh, because there's always going to be some of the old transmission fluid still in the transmission. So this is kind of a similar idea, that after the hydraulic retention time, it's not like it's pure water, because you still have some of the tracer remaining behind. An F curve, on the other hand, remember, that's the fraction that has exited over time. So a completely mixed flow reactor, 0 has exited, but it's going up steeply at first, and then it gradually starts tapering off as the concentration becomes more dilute inside of the completely mixed flow reactor. So you could sketch the F curve by knowing the initial amount and then the amount that remains over time. So for ideal behavior, it would look like this, with 63.2% remaining after the hydraulic detention time. I'm sorry, 63.2 has exited after the hydraulic detention time. So again, this is just talking about if you wanted to solve for the hydraulic detention time, then you could do an experiment. Like if you didn't know the hydraulic detention time of a system, you could see how long it takes, if it's completely mixed, to get the concentration down to a certain known concentration. So you could say solve for theta, and then you could put in known concentration, initial, an elapsed period of time t, and then the concentration at that time you could measure. And that would be one way to solve for the hydraulic detention time. So we've already talked about how you'd have in a plug flow reactor, it's broader when it is subject to more mixing, and it's more tight and peaky if it is tending towards an ideal plug flow reactor. These are called arbitrary flow reactors, where this is a plug flow reactor that's having some short circuiting and is experiencing some dispersions. It's a plug flow reactor, but it's just not behaving like the ideal. And here's the ideal for a completely mixed flow reactor. And this is kind of weird. Look at how it's starting at 0 and it's going up before it's going down. So why would it be going up for a little while before it goes down? Well, think about the way that we test this. We've got a tank full of some liquid. We're injecting the tracer, and then maybe we have a sample port down here where we're taking it out. And since this is a completely mixed flow reactor, there's also liquid coming in. So there's flow going in. We drop our tracer all at once, and then this is the sample port where we're testing the stuff out of here. So this is our completely mixed flow reactor. Why do you think that we would see an increase in the actual concentration before we see it start decreasing? Any ideas about that? Yeah.
Well, the ideal says that it instantaneously disperses, but we know that's not actually what's happening, so it takes a minute for it to actually
Perfect.
disperse.
That's it 100%. She's got it exactly right. That, we've got this mixer and it's dispersing it, but okay, so we drop it in, it's a little bit dispersed, it's a little bit more dispersed, 3 seconds later, 4 seconds later, 5 seconds later, and so then a little bit of it is coming out of the sample port, but then still most of it's over here. So it's kind of like gradually getting towards the sample port slowly, and that's what this leading portion of the curve is showing, is just that it's not being instantaneously mixed. And this is what we're seeing is dispersion, and we're seeing mixing inside the reactor. That's what causes the deviation from ideal in a plug flow reactor. The deviation from ideal is the plug flow reactor assumes that once something goes in, there's no mixing. But actually there is mixing, and so it deviates from the ideal because there is really mixing. Here, in a completely mixed flow reactor, the ideal is it's mixing so well that as soon as it gets in, it's instantly everywhere. That's not true. So this actual just is representing that. Completely stirred tank reactors in series. If you have a series of completely mixed flow reactors, that's the same thing as a plug flow reactor. If you had an infinite number of them, then that actually will behave as a plug flow reactor, because you'd put it in and it would stay in one, but it wouldn't yet be out at the furthest most one. So it's just kind of interesting that if you want to have the benefits of a plug flow reactor, what you do is you'd have a series of completely stirred tank reactor, completely mixed flow reactors, one after the other. And we'll do that in environmental engineering. We'll have some examples this semester where we have a series of these reactors. In a consumption reaction with reactors where we're using K values, I wanted to tell you about the temperature sensitivity to reactions. This is kind of just a generalized expression that can help you tell how the K value changes as a function of temperature. And not all reactions follow exactly this behavior, but it's in general, chemical reactions are faster in warmer temperatures, and definitely biological reactions are faster in warmer temperatures. So if you know the temperature in Celsius, then you can use this to find the K value at some temperature other than 20. So K naught here would be what's the reaction rate constant at 20 degrees, and then you could correct for a reaction rate constant at a different temperature. Okay, this example we didn't have time to do today. I'm going to have to take a look at what we're covering on Wednesday and decide whether to pass it to Wednesday, or I might email this one to you. So be sure to check your email later today, and then I might email this example to you. All right, see you Wednesday, or maybe in 10 minutes next door.